So, hi everyone, I'm Andreea Petric. I'm an associate scientist at Space Telescope. And I have the pleasure to talk to you today about the wonderful things that Raman deep grid spectroscopy can do for the study of active galactic nuclei. The background image that you will see throughout my presentation is a simulation of the beautiful spectra that we expect to gather with the Raman GRISM. And the image next to the author list is a beautiful simulation of two galaxies like the Milky Way and Andromeda that in a couple of billion years will merge, and the central supermassive black holes in both galaxies may receive an additional amount of gas that will transform them into active galactic nuclei visible from a galaxy far, far away. And so the Spitzer telescope revolutionized our understanding of galaxies. Here you have a composite of observation from this infrared with the Spitzer telescope of nearby galaxy, a survey legacy program that has shown many details in galaxies and morphologies that are quite different. However, what is common in all those galaxies is that if we look deep enough, we detect a supermassive black hole at the core. And what is more surprising is that the mass of that central supermassive black hole is correlated with the mass of the central bulge. And while galaxy mergers can explain this correlation, the scattering in the correlation, which is larger than measurement errors, reflects a need for other mechanisms such as feedback, the exchange of energy between the either growing supermassive black hole or the star formation processes. So those processes can explain the scatter and reconcile the observed galaxy luminosity distribution with simulated galaxies, simulated luminosity galaxy functions, galaxy luminosity functions. So we've mentioned that there are all those black holes, but where, when, and how were all these forms? So this plot shows you the various scenarios that can lead to the observed distribution of black holes and their host galaxies. But it is important in order to understand those various scenarios and be sure that we choose the correct one, that we have detected all the black holes, or at least that we have detected the representative types of black holes in various range of both redshifts and galaxy luminosities. So it is important not to systematically miss black holes. So for a long time we were missing obscured AGN, and with the arrival of all sky mid-infrared surveys, we were able to find obscured AGN that were not easily detectable in optically selected surveys. So on the left, you have such example of color selection criteria that allow you to pick the warmest gas and dust and differentiate from other kind of galaxies, those that may have an AGN. And on the right-hand side, I show you a sample of mid-infrared selected AGN detected by Spitzer that were followed up with optical and near-infrared spectroscopy and separated into different types. And this work took years. But what we seem to find is that the luminosity function of different types of galaxies is different. And not only that, but at higher redshift, we seem to see that the evolution of obscured red type 1s and type 2s may differ from those of normal unobscured type 1s and all quasars in general. So it appears that there is a difference between the obscured and unobscured AGN, and that this difference increases at higher redshift. And the reason that this is important, that we do not miss those galaxies at redshift 2 and 3, is that it so far appears that a lot of the growth and activity in galaxies happens at this redshift, known as the cosmic noon. And so combining a Raman imaging and slitless spectroscopy with the faintest, with objects of H-band magnitude on the order 24 and 26 will be a powerful way to study obscure galaxies and the processes that shape them at redshifts where galaxies were most active. So one way that dusty galaxies are exciting is that they probe one of the scenarios that explain this correlation, which I showed you earlier in the talk. So one way to explain this this correlation and the scatter associated with feedback is starting from a scenarios in which gas-rich mergers evolves into obscured AGN, and as the central supermassive black holes grows, and either it impacts the surrounding interstellar medium, either by pushing the gas out or heating it and making it unlikely to form new stars. So as the core material is being depleted, we are able to clear the path also for broadline emission. And as time progresses and the path is cleared more and more, no additional accretion is being put toward the center, and there's also less star formation, what is known as the quenching of galaxies. So in this scenario, obscured AGN are quite important. And I must say that this is not the only scenario that explains either the quenching of galaxies or this correlation between the central supermassive black hole and the host galaxy. But this is an important one, and we know it is because we can see images that are such as the train wrecks that you see at the top left of this image that shows that gas-rich galaxies merge. And there is additional evidence that I will show you later. So it's important to study obscured AGN because they may represent a significant step in the evolution of all galaxies. And in addition to our originally posed reason, which is that we want to find all the black holes, especially we want to find all the ones that are growing, either they are obscured or not obscured. And so some evidence of this scenario and of this important stage came from high redshift HST observations by Glickman et al. Of quasars at redshifts greater than 0.7. So what they were able to find is that the most luminous galaxies, the most luminous dust-redden quasars were mostly mergers. Now with Raman, we will find and study more of such objects and be able to increase our understanding of this process at high redshift. Also, we will be able to explain why not everyone sees this, why we do not appear to see this at lower luminosity. For example, Lambrides et al. 2021 find that at lower luminosity, so here we're going by a factor of 10 to 100 lower luminosities, when we compare the merger fraction in obscured AGN, find as such from X-ray observation, we see that the merger fraction relative to a control sample is higher in lower luminosity, in lower redshift sources than it is at higher redshift. And so one question here is why this is, or whether we are missing the faintest, most obscure AGN at higher redshift. With Raman, we will be able to find and study those faintest sources Now, in the nearby universe, when we look at gas-rich infraluminous galaxies, and some of the beautiful images of merger galaxies that I showed you earlier in the talk come from those nearby luminous infrared galaxies. So when we look at those with Spitzer and with Hubble, we find that we can separate the fraction of infrared emission that comes from the AGN versus star formation by a whole range of diagnostics that are available in mid-infrared spectroscopy, and that will be available with significant improvements in spatial and velocity resolution with JWST. So we separated the contribution of AGN into the IR and starburst. So the starburst is in blue and the AGN is in red, and we separated them by different merger stages. And those are those examples of such morphologies are showed at the bottom of the histogram. And what we find, which confirms other results, is that the AGN fraction is relatively higher in mergers than it is not in non-merger. Now, these were very nearby sources, and with Roman and JWST and other ground-based facilities, we will be able to do such studies to much higher redshift. So another question, besides finding all the AGN, finding all the obscured AGN, seeing what is the interplay of merger, is how do galaxies evolve? And the question of how do galaxies evolve is closely linked to the question of what happens to the interstellar medium. With Spitzer, we were able to look at various transitions of warm molecular gas, and in some cases, where we had sufficient velocity, where we even at Spitzer's velocity resolution, we were able to find sources with broader profiles than their resolution, and we found that those broadest profiles seem to come from AGN hosts. But now the sample was small. Yet it was significant. It seemed to suggest that AGN did something to their host galaxy. And again, it confirmed what previous work, even from ISO and Spitzer on nearby galaxies, was finding. However, we need a larger sample. So we took everything that Spitzer had observed, that Spitzer infrared spectrograph observed, and we did the same study, and we find with a very statistically significant certainty that AGN had warmer molecular gas, and that this was not an effect of the merger. Others followed those up with SDSS spectroscopy and found that the H2 axis seemed to be associated with outflowing gas. Now, Roman will be simultaneously able to study the morphologies as well as the warm-hot gas properties of AGN hosts, and be able to delve deeper into what was happening in those galaxies. Since it is an essential question of not only are we counting all the AGN, but why is it so important to count the AGN? What do the AGN do to the host galaxies? And so that's one question, what do they do to the host galaxy? But other questions are connected to the study of the circumgalactic medium. We followed some of those nearby luminous infrared galaxies with spatially resolved spectroscopy and found 30 to 40 kiloparsec range structures of ionized gas moving at speeds showing evidence that they were able to throw out such material from the galaxies, and therefore enriching the circumgalactic medium. So with Roman, we can answer all those questions at once. So first, where can we look? Again, this is the plot that I showed you early on with the differences of mid-infrared selected AGN. And so ideally, we would go to a field that has been observed by Spitzer or will be observed by the James Webb Telescope in order to connect the morphologies with mid-infrared selection and also radio. And so the wide field of the GRISM will allow, and the sensitivity and wavelength coverage will allow us to find sources that have been observed and detected as such in the radio. So the radio is a significant factor because jets associated with AGN have shown to impact the host and galaxy evolution. So following fields with high sensitivity radio studies will be important. So one of those, there are several radio programs throughout the world that are preparing for the square kilometer array observations in both at both low and frequency and high frequency, allowing us to trace the electrons that are being sped up by processes associated with the AGN. A current survey in the very large array, Sky Survey, will be fantastic as it allows again to determine accurate demographics of radio loud and quiet populations. And with Roman, we will be able to connect the processes that we will only able to see in the optical and near infrared with this radio jet energy. Also, it's important to understand that Roman superb spatial resolution and sensitivity will be also essential to understand observation, the torrent of data that is going to come from eROSITA, an X-ray mission that will allow us to find the most obscured AGN, including sources that have been so far quite elusive, like the Compton-thick AGN. And so to end, Roman will be fantastic. In about 5 days, Roman will be able to reach the same sensitivity as some of the most influential near-infrared GRISM surveys done with HST treasury programs, and they will be able to do them in a wider area. So Roman's superb spatial resolution and sensitivity will allow us to connect our observations with radio data and estimates of jet kinetic energy, to simultaneously study AGN and environmental feedback, and to do a census of shock molecular gas in nearby AGN. Thank you.